We can make matter hotter than a star's core and colder than interstellar space. Physics limits temperatures between absolute zero and the Planck temperature. This video shows those extremes and what they actually mean. Right now, you'll get a clear map of temperature's true edges. Picture a room full of bouncing atoms, each moving with its own speed. Temperature measures the average kinetic energy of those particles. Knowing extremes matters because energy scales change how matter behaves. At low temperatures, quantum effects dominate and motion freezes into waves. At high temperatures, particles collide violently, creating new forms of matter. For example, mercury in a thermometer expands as molecules move faster. So temperature is energy averaged across particles, and it sets behavior. Far below freezing exists a limit called absolute zero. Absolute zero is the point where particles have minimal quantum motion. Reaching it unlocks exotic physics and ultra-precise technologies. As temperature falls, particles lose kinetic energy and quantum ground states appear. You cannot remove all energy because quantum uncertainty prevents complete stillness. Laboratories cool atoms to billionths of a Kelvin, forming Bose-Einstein condensates. Absolute zero is a quantum floor, not a practical zero of motion. Some systems can reach negative temperatures on the Kelvin scale. Negative temperature means the system stores more energy than any positive temperature. This flips intuition, because negative temperatures behave hotter than infinite temperature. It requires an upper bound in energy and a population inversion. Lasers and certain spin systems achieve this by flipping occupancy of states. Researchers created negative temperatures in cold atoms and nuclear spins. Negative Kelvin values are exotic, and they are hotter than any positive temperature. In stars, crushing gravity heats gas to millions of Kelvin. Stellar core temperature is the average particle energy driving fusion. Fusion temperatures determine whether stars live, die, or explode. Gravity compresses the core, and pressure raises thermal energy. At about 10 million Kelvin, hydrogen nuclei can overcome electrostatic repulsion to fuse. The sun's core sits near 15 million Kelvin, powering sunlight for billions of years. So stellar temperatures are extreme, yet far below particle physics maxima. When massive stars die, temperatures spike into the billions and beyond. A supernova briefly heats matter to tens or hundreds of billions Kelvin. Those temperatures change chemistry and seed the cosmos with heavy elements. Core collapse releases gravitational energy, and shock waves raise temperatures. In neutron star formation, densities and heat produce neutrino-driven reheating. Measured supernova remnants show early temperatures near 100 billion Kelvin. Supernova heat is brief, yet it forges elements and reshapes galaxies. Colliders recreate temperatures trillions of Kelvin for microseconds. A quark-gluon plasma is matter so hot quarks roam freely. Studying that state tells us how the early universe evolved. Smashing heavy ions deposits huge energy densities in tiny volumes. The energy overcomes confinement, melting hadrons into their constituents briefly. At the LHC, temperatures reach about 4 trillion Kelvin in collisions. Quark-gluon plasmas show matter's laws shift at extreme energy. Physics predicts a maximum temperature called the Planck temperature. The Planck temperature is about 10 to the 32 Kelvin. Above it, our current physics breaks down entirely. At this scale, gravity and quantum effects are equally strong. Spacetime fluctuates, and known equations fail to describe conditions. The Planck era lasted tiny fractions of a second after the Big Bang. So the Planck temperature marks a frontier beyond current theories. We saw temperatures from quantum cold to Planck hot and why they matter. Remember, physics bounds temperatures between absolute zero and the Planck temperature. If you enjoyed this curious tour, consider subscribing for more clear science. Bottom line, physics sets the coldest floor and the hottest ceiling.